Alright guys, so this is the first video for equilibrium. So it's just the introduction. It's pretty straightforward. Alright, so chemical equilibrium, you can also see it called dynamic equilibrium, is where the reaction doesn't go fully to completion. It sits somewhere in the middle. Alright, so if we look at this reaction right here, we have nitrogen dioxide and it's turning into dinitrogen tetroxide. And we have these arrows here, which means an equilibrium exists. All right, so this substance right here is really dark brown, and this substance right here is colorless. And so if you look at these vials down here, those are all the different stages that the reaction can go to if forced a particular way. At room temperature, it sits right here. So it doesn't matter if we start with this or if we start with this, we'll end up here, which is a mixture of both of them. Some reactions lean more toward product and some reactions lean more toward reactant, but we have a numerical value that tells us where the reaction is going to sit. And that's what we have to learn how to use. So before, if you would have started out with 5 grams of this, you would have been able to tell me how many grams of this would be produced by using molar mass and mole-to-mole ratios. We can't do that alone with equilibrium because it doesn't all turn into this. It stops somewhere in the middle. So we have to be able to figure all that out. So dynamic chemical equilibrium. All right, if we look at the graph here on the left, we haven't started out with any product, right? These two here are products in this reaction, the way that it's written. We didn't start out with any product, but we did start out with reactant, the purple one. All right, and we started out with 0.01 molar. And so that concentration is decreasing as time is going on, and the concentration of the products is increasing. Okay, now we get to a point where they stop changing, and it's about right here at 500 seconds. So the NO2 has not completely all gone away. It's still present in quite a bit of amount. All right, while NO and O2 have increased to a point and then they stop increasing. So we could make more of these two, but it doesn't do that for some reason. All right, and then if we perform the same reaction, but this time we're starting out with NO and O2, they start all the way up here, and NO2 starts all the way down here. So we don't have any NO2. And we end up getting to a point again where the products do not all disappear. They still stay in concentration. And we've made a certain amount of reactant here. Okay, and still the amounts of product and reactant stop changing around 500 seconds. So at this time, when these concentrations stop changing, we've reached equilibrium. We don't run out of reactant, it still stays, and we don't run out of product if that's what we started with, but we don't see a change anymore in the amount of reactant and the amount of product that is produced. All right, and so the actual definition of chemical equilibrium, if you remember in kinetics, when we were looking at mechanisms where the second step or the third step was the slow step, and it usually had a fast equilibrium step that preceded it. So what we said was that the rate of the forward reaction is equal to the rate of the reverse reaction when equilibrium is achieved. And that's what we're seeing right here with this graph. So if I look at this right here, if this is the forward reaction, NO2 is being consumed at the rate of the forward reaction, and here NO2 is being produced, right, the same rate as the reverse reaction. So we get to a point to where equilibrium has achieved. So this right here shows that equilibrium is achieved. So the rates are the same there, and they're constant, right? So rate is going up here on the y-axis. All right, now I want to clarify something. That does not mean that the products are equal to the reactants. It's the rate that the products are being produced is equal to the rate that the reactants are being produced. So the forward rate is equal to the reverse rate. You cannot say that the concentrations are always going to be equal to each other. If this is our general reaction, all right, so we have our reactants and we have our products and we have certain coefficients for each one of those. Then this right here is called our equilibrium expression. And so you see here we have products, C and D, raised to their coefficients. So C's coefficient is M, and that's what it's raised to. D's coefficient is N, and that's what it's raised to. And then there's over the concentration of the reactants raised to their respective coefficients. Okay, and so remember these brackets are molarity and molarity only. So it has to be molarity that you're plugging in. And not only that, but the molarity at equilibrium. So the concentrations that are used to find this K value is at equilibrium. And this K value is called the equilibrium constant. Okay, it's big K. It's not little k like in kinetics. And big K is completely unitless. And it has to do with thermodynamic and standard states, and we don't talk about that. But you don't get it mixed up with baby K. Okay, baby K is for kinetics, and it has all these units associated with it that you have to calculate, but you don't have to do that with big K. You just plug in the numbers and get it, and that's it. All right, so if we wanted to put this into words, we would say K is equal to the products raised to their coefficients divided by reactants raised to their coefficients. There's no plus sign in it. It's always multiplication and division. And as a side note, only gases and aqueous substances are put into equilibrium expressions. We'll cover that more later. Right now, just worry about writing them and calculating Ks. All right, so why do we call it the equilibrium constant? Well, we call it constant because it's constant. The only thing that changes it, just like baby K, is temperature. As you can see from this table, if these are our initial concentrations, so they're not used to find K. The only thing that's used to find K are equilibrium concentrations. But the initial concentrations are put into this table so that you can see what's happening here. All right, so they're not used to find K. They are only here so you can see something. So in this first experiment, we started out with N2O4, the product, and none of the reactant. And at equilibrium, we get these concentrations for them. All right, and so if we wanted to calculate K, K would be calculated by taking N2O4 concentration and then dividing it by NO2 squared. And so that's this right here. That's the expression. And so if I do that, if I take this and then divide it by this squared, I get 216. Now in the second experiment, we did the same thing where we started out with 0 of the product this time and 0.08 of the reactant, and we ended up getting the same numbers. So we get 216. And then in the third experiment, we started out with 0.06 of the product and 0 of the reactant, and we get these numbers, but it's the same, pretty much the same ratio. Same with this one, same with this one, and in experiment 5, we started out with both reactant and product, and we still ended up in the same spot. So that's why this is considered a constant, and it tells us a lot about the reaction, which we'll dive more into later. All right, so if we want to write the equilibrium expression for this reaction up here, K would be equal to, and we're going to take our products raised to their coefficient, so it would be NO2 to the 4th times H2O to the 6th divided by NH3 to the 4th times O2 to the 7th. All right, and then if we wanted to reverse this expression for number 2, then I would end up flipping this thing over, right? So I could say, and I'm going to call this K, K prime, all right? So that's like a little apostrophe. The expression would be O2 to the 7th times NH3 to the 4th over H2O to the 6th times NO2 to the 4th, right? So that's flipped. You could also say that it's equal to 1 over K, because if we take this one and we invert it, then we end up with this right here. All right, and so if all the coefficients were doubled, then what we'd basically be doing is multiplying all these by 2, right? Because this would be 8, and this would be 14, and this would be 8, and this would be 12. And so whenever you multiply an exponent by 2, you're squaring it, right? And so what we would end up having, you're squaring this whole value, you would end up having K double prime is what I'm going to call this one. And that would be equal to H2O to the 12th times NO2 to the 8th divided by O2 to the 14th times NH3 to the 8th. And so that would also be equal to K squared, the original K squared, because all of these values are squared. All right, in this last example here, we want to calculate the value of K at 127, and the only reason they tell you it's 127 because if temperature changes, these K's change. All right, so we're keeping it constant. These are the equilibrium concentrations, and the synthesis of ammonia is this reaction, and all of these are gases. So I'm going to write my equilibrium expression first. So I have NH3 squared divided by H2 cubed times N2. So then if I go and plug all my values in, I get 3.1 times 10 to the negative 2 squared divided by H2 3.1 times 10 to the negative third cubed times 8.5 times 10 to the negative 1, or 0.85. So if I put this into my calculator correctly, what I end up getting is 3.8 times 10 to the 4th. Remember, there's no units. So that's it. That's my K. All right, and then the value of the equilibrium constant at 127 for this reaction. So this reaction is the reverse of this. So I could, so this is B, flip it all over and put it all in my calculator again. And you can try this if you want. Or I could just say it's the inverse of this, because all I've done is flip it over. So I end up getting 2.6 times 10 to the negative 5th. Okay, and then this last one, calculate the value of the equilibrium constant at 127. We have this. So I've halved all of the coefficients from the original reaction. So if I'm going to half all of these, this one is halved, this one is raised to the 1/2, and this is halved. Whenever you have something raised to the 1/2, that's the same thing as taking the square root. So I'm basically taking the square root of all of these, which means I'm taking the square root of K. All right, so this K double prime is going to be equal to the square root of K, which is equal to the square root of 3.8 times 10 to the 4th, which is going to be 1.95, or 2.0 times 10 to the 2nd. That's it. It's as easy as that.